Well, that was fun. Well, I don't know if that's the right way to describe it, but what we did here was we projected one vector onto the span of one other vector. But the span of one vector, in the previous example B, is just really a line, right? You can walk as far in the direction of B as you want in either, in the forward or backwards direction, but you can't really change where you're moving. Like you can walk this way or you can walk this way, basically, right? What I want to look at now, which is perhaps more fun, is the span of multiple vectors. So now let's pretend we have two vectors, x1 and x2. Note that these parentheses up here are not exponents. I'm just using that to denote one x vector and another x vector. Okay? And what I want to consider is projecting y onto the span of x1 and x2. Okay? And remember, the span of x1 and x2 is the set of all linear combinations of x1 and x2. And a linear combination of multiple vectors is any vector of the form number times the first vector plus number times the second vector plus, if there were more vectors, number times the third vector, and so on and so forth. Okay? And just to make things interesting, what I'm going to do is work with vectors in at least 3 dimensions. Okay? Because if I had 2 spanning vectors and I was working in 2 dimensions, then as long as the 2 spanning vectors weren't in the same direction, I would be able to span all of the 2-dimensional vectors. Right? And this is something we explored last class. And if I can span all the 2-dimensional vectors, well then the projection of y onto the span of those 2 vectors is just y exactly, because I could recreate y exactly. Okay, but that's not often going to happen in practice. And so what I'm going to work with, at least just have this picture in your mind, is that I have 2 x vectors that are 3-dimensional and a third y vector that's also 3-dimensional, which means in most cases you can't recreate y exactly using your 2 x vectors, which was the case in the previous slide as well. Like I wasn't able to recreate my y vector exactly, I just had to get as close to it as I could. Okay? And so to really drive home what's going on here visually, I'll pass it over to Jack, who will talk about this animation that he created for this exact idea.
Thank you again. Hopefully I don't mess up the thing this time. All right, hello guys. Can everybody hear me well enough with the mic like this? Okay, cool. I got nods this time, which is good. Okay, so yeah, just reiterating quickly what Suraj said. I can just click play and then pause. Okay, cool. What I'm going to be showing is the projection of a vector y in 3 dimensions onto the span of 2 other vectors in 3 dimensions when we can't exactly recreate y with a linear combination of these 2 vectors. And so hopefully this will help you build some geometric intuition to what's going on here. As we can see, I'm just going to walk over here real quick. We have this time 2 parameters we can tune when we're scaling our 2 vectors, because we are not just dealing with the span of 1 vector, we're dealing with the span of 2 vectors. And as these coefficients change, the linear combination of x1 and x2 also changes correspondingly. And if we were to visualize this span in 3 dimensions, what it would look like is a plane like this. And as you can see, this plane does not actually contain the vector y that we're trying to project onto the span. And so what we need to do is find a vector that is the closest as we can get to y. And as we just proved, this is the orthogonal projection of y onto this span. And this is just the translated version, again, of that concept into 3 dimensions. And so to further drive home this point kind of visually and heuristically, if we change this projection and make it somewhere else in the span of x1 and x2, we can visually see that this error vector representing how far our projection is away from y is just visibly much larger in magnitude than it was when we were looking at the orthogonal projection of y into the span of these 2 vectors, which we can see again here. And so this happened last time too. Just a very important concept to have a picture of in your mind, like a very clear geometric interpretation of what's going on, because as we move into higher dimensions, it's good to have a solid foundation and understanding, both mathematically, which is what we just showed, and visually, of what we're really talking about when we say that the orthogonal projection is the best projection of y into the span of another set of vectors. So thank you guys. I'll pass it back to Suraj. Oops. I just dropped your pen. Hopefully the tip didn't break again.
Hopefully. Cool. So, as Jack mentioned, what we are now looking for is the vector in the span of x1 and x2. And remember, the span of x1 and x2 here is a plane rather than a line now. We're looking for the vector in that plane that is as close to y as possible. Okay? And vectors in that plane are written in the form w1 x1 plus w2 x2. So the question really is, what is the best w1 and best w2 to choose? Right? And the answer is that I'm choosing the w1 and w2 that make it so that my error vector, which is this thing, is orthogonal to the span of x1 and x2. Okay? The error is orthogonal to the span of x1 and x2. Right, that's what we saw in that animation. The shortest possible error vector is the one where that red error vector, the red line, is perpendicular to the plane of all possible x1s and x2s. Or combinations of x1s and x2s. Okay? And so, what I've written here is w1x1 plus w2x2, and the point is that any vector in the span of x1 and x2 can be written in this form. Right? And so what I've written first is a vector in the span of x1 and x2. And what I've written second is the associated error with that vector. Okay, it's saying, okay, if I choose w1 and w2 as being my linear combination coefficients, well then the associated error will be y minus that thing that I have up front. And the goal is to make my projection w1 x1 plus w2 x2 orthogonal to its error. Right? And in order for it to be orthogonal, well, the dot product of my projection with its own error should be 0. That we've proven already in the two-dimensional case, and it expands in n dimensions. You really just draw the same picture. Okay? Now the issue is that solving for w1 and w2 here is kind of annoying. That's really the crux of the issue. Like if I could do it very quickly and find what w1 star and w2 star are supposed to be, we could call it a day and move on, but we can't really do that here. Okay, but there's one way to simplify it. And the simplifying step that we will use for the rest of the lecture is that trying to solve for w1 and w2 here right off the bat is kind of annoying, but there's a simpler assumption I can make. If all I assume is that the error vector is orthogonal to x1 and orthogonal to x2, that is orthogonal to the two spanning vectors individually, it turns out that just by assuming those two things, this statement also holds true. So it's a way of decomposing this big equation into two smaller ones, okay, which perhaps may be easier to solve. And what I want to prove to you is that this being true and this being true implies that this is true, okay, meaning that they're equivalent. Okay, or at least all we have to really think about is this. Let's think about what w1 x1 plus w2 x2 dot producted with my error vector might look like. How can I simplify this? Well, and notice this is exactly what I have here. I can use, again, the distributive property of my dot product. I can write this as w1 x1 dot e plus w2 x2 dot e. Okay? Now, we'll recognize a few terms that we know something about. What is this thing? Zero, right? And what is this thing? Right, we're starting with the assumption that they're both 0. Okay, what's the key takeaway here? It's that I don't have to jump to assuming that w1 x1 plus w2 x2 is orthogonal to the error vector. It's easier to just assume that x1 and x2 individually are orthogonal to the error vector. And if that's true, well then this is also true. Okay, so this is a simpler way of thinking about this big equation up here. x1 and x2 are individually orthogonal to the error vector. Okay, and the conceptual way of thinking about this is that if I want my projection to be or my error vector to be orthogonal to the projected vector, it's equivalent to just thinking about my error vector being orthogonal to the spanning vectors individually. So that is, if the error is orthogonal to x1 and orthogonal to x2, well then it's orthogonal to any linear combination of x1 and x2. Okay, that is, if the error is orthogonal to x1 and orthogonal to x2, then it's orthogonal to anything on that plane spanned by x1 and x2. Okay? And so my problem of finding the vector in the span of x1 and x2 that's closest to y has been simplified to finding the w1 and w2 that satisfy this system of equations. If I can solve for w1 and w2 here, well then I can express the vector in the span of x1 and x2 that's closest to y. Okay? Because it would be w1 times x1 plus w2 times x2. That's my goal. I want to find the best w1 and the best w2. Okay? Now I have a system of two equations and two unknowns, but it still looks annoying to solve. We agree? And in particular, it's annoying, but it would get linearly more annoying the more spanning vectors I had. Right? If I had 3 vectors whose span I wanted to project onto, or 5 vectors whose span I wanted to project onto, well then I might have a system of 3 or 5 equations and unknowns. And that will get really messy to solve for w1 star and w2 star and so on and so forth. And so what we're going to try and do is rewrite this system of equations and unknowns using matrix vector operations. And when we do that, we will be able to express it as a single equation that we can then solve for. Okay? And so we're going to revisit this idea of projections and spans, but first we have to go on this brief diversion involving matrices. Sound okay? All right. But any questions with what we are trying to do here? We are trying to find the vector in the span of x1 and x2, which again is a plane, that is closest to y. And we've proved that the vector in the span of x1 and x2 that's closest to y is the one whose error is orthogonal to the span of x1 and x2. And so the problem really boils down to finding the w1 and w2 that make this happen. And to do that, we need matrices.